Okay, sorry. I know we're running late. Let me just move this around. Okay, hello everyone. And wow, that is a fantastic pyramid you all managed to make today. Your like names all got slightly shorter, so it actually ended up like a very professional looking pyramid. Well done. Hello everyone. So, welcome to our 2-slide lecture. um, the reality of things this week is that I mean, it might genuinely be like the time to sort of give all yourselves like a pat on the back for having made it this far, because we're really towards the tail end of the course now. I think last lecture was really like the sort of big culmination of stuff, talking about how Rust manages like all these sort of things we've learned about come together to provide us safe concurrency, which again, as we talked about last lecture, is a growing and growing. It's growing and growing in size in the industry, and more and more things are becoming increasingly concurrent. And so to be offered that kind of safety and assurance in a concurrent setting is something that I think, at least I think, is very valuable. Yeah, I mean, we talked about most of the concurrency stuff. It would have, there is a whole sort of separate section of Rust known as, if you've heard of like async Rust. What we're doing here in the concurrency topic is asynchronous, but it's not like async in the sense of async Rust. It's a slightly different thing. Something that I regrettably believe that we don't have time to talk about in this course. Although, if we can find a way to slot it in somehow, then, it'd be fantastic, because it's another sort of really interesting another really interesting thing that Rust has a lot to say about naturally. But yeah, we really covered most of the big ticket items in concurrency in the Monday's lecture. Talking about concurrency in general, how it works. We looked at threads. We looked at the bounds on a thread spawn closure. It was fn once plus send plus tick static. What else did we look at? We also looked at scoped threads. As a reminder, stood F. That's a real thing apparently. Docs RS stood. There we go. We looked at scoped threads, which was where this signature has been changed a little, such that now you can borrow things from like your outside scope, like say in main or something like that. Whereas previously when we tried to borrow things from main, it would always tell us, hey, the thread might outlive main, and so you can't borrow stuff from main. And thread scope was a nice tool that basically said you can spawn threads within this scope. And through that, you can then borrow things from main, like this A variable here. Borrowing's all fine, the lifetimes all check out, because one of the really important things thread scope does is for all the threads that you spawn throughout it, right? A thread spawned here, a thread spawned here. Once the scope reaches the end, there is an implicit join on all threads that you've spawned, which means main is going to sit right here waiting for both of these threads to finish before it continues on. And as such, Rust is able to guarantee safety in terms of the borrowing, because these essentially these threads cannot outlive the outside scope, which is why we call these thread scope. We're essentially limiting the threads to this sort of inside scope here. And if you plan to just join on all the threads you spawn anyway, like if you're sort of doing like a spawn, a whole bunch of threads, and then join all the threads, just sort of hoping for all those threads to, run concurrently with each other, then this also saves you having to like remember all the threads in a vec and then join all the threads afterwards and all that. Instead, you just get to It just sort of does it all automatically for you, and you get the bonus superpower of borrowing from the environment. And I mean, I don't know if we looked too closely at this signature here, but really all it's saying is scope defines this tick env, right, which is a lifetime relevant to the environment, and then you provide a function f, that would be this one here. This is just a function that will only be run once, and this is just run on the same thread. It's run on, let's say we're in the main thread here, it's just run in the main thread. These here are where we're actually going to end up with other threads coming about. And it's simply a function. I mean, it can produce a t, but we don't really, it's just to sort of passes this t along. We don't really need to worry about it. And it just says this function should be able to take a scope in. Scope has two relevant lifetimes, tick scope, tick env, which we'll be able to look at if we look at the scope type. Note that it is a borrow of a scope, right? This S here is a borrow, and that borrow must be valid for any lifetime tick scope. We haven't really seen this syntax here before. It's something called higher ranked trait bounds. It's a little complex, and I don't think you should need to run into this in the course yourself, but it's essentially saying this FN must satisfy the like wherever it uses the tick scope lifetime, which is here and here, it must be able to, like, it must be valid for any lifetime tick scope. It's occasionally it comes into use, but again, we shouldn't need to use it ourselves in this course. But then the important part here is looking at how things like scope and that relate. And so we know that scope maintains the lifetime of the scope and the lifetime in the environment. Notably, the lifetime of the environment outlives the lifetime of the scope, right? So lifetime of the environment, lifetime of the scope, right? And it says that when you want to spawn a thread, right, within this scope, you give it an F. That F is an FN once that is, produces a T maybe if you want it. Again, we've seen how it passes the T through. But the important bounds here are not send and tick static anymore, like a normal thread spawn. It's now send and tick scope, which is cool. So now we can actually borrow from the outside scope. And again, the whole reason that like Rust didn't do this for the standard thread spawn and it was able to do it for the thread scope is because, they had to think about the lifetimes and go, is there ways that you could, run into memory unsafety or lifetime issues? With thread spawn, there's very little guarantees about what happens with that thread after you spawn it. And so they have to be very conservative. Whereas thread scope, it has this sort of built-in nature where it will wait for all the threads to finish. And thus it's sort of more restrictive in what it lets you do with the threads you spawn. But in that greater restriction comes more flexibility in what it's certain that you could do in these threads that will always be safe, and also potentially a bit of convenience if that restriction is something that you planned to already enforce yourself. But now there's additional reasoning that can come along with that restriction that you can take advantage of, that you wouldn't really be able to, like the compiler won't do any sort of crazy reasoning to go, I know the thread could maybe live on, but they do join it there, so I'm just gonna I'll say it's okay this time, I'll let this one slide. I think we're all very familiar with the thought that Rust is very rare to say things like I'll let that one slide. So we learned all about scoping threads and all that. We also talked about send and sync, those traits. We'll probably be talking about them a little more today, but the main idea being a type T. These are like automatic traits, so you don't implement them yourself. The compiler looks at what's inside your struct or what's inside your enum and derives it based off that. And they're both marker traits. They don't define any like methods like most traits do. Like the clone trait says you need to implement the clone function, or the iterator trait says that you have to implement the function next to get the next item from the iterator. These don't define any functions at all. They're just used to sort of mark that a type is okay in some context. And in particular, send denotes the idea that some type is safe to be sent from one thread to another. right? So like, for example, a string is send, and that if I have a string on thread A and I go, actually, I'm done with this string, I'm going to send it over to thread B, and it can own that, that's fine. We can send it from thread A to thread B, and it'll have no problem with that. And then things like the sync trait as well. So, I mean, send and sync really come in a close pair. Sync specifically meaning, is it safe to send? Like if I have some type T and I want to know, is T sync? Well, the question is it safe to send a borrow of T? Right? This is to be clear, a shared borrow, a read-only borrow, a shared reference, whatever you want to call it, right? What's the other one? Immutable reference. You know, whichever terminology you have, then be comfortable with that. But whether it's safe to send across a thread boundary, a borrow of the T that we care about, a shared borrow. And I guess like send and sync are more interesting in the things that don't implement them rather than the ones that do, given like the set of types that implement send and the set of types that implement sync are quite large. And the set of types, but you know, however, the set of types that don't implement them is more constrained. And so maybe we'll also play around with a couple types that don't implement send and sync, or maybe think about like, you know, why would it be dangerous for said type to implement send and sync? And we still have a couple other things to look at. So here's our to-do list. Move closures are something a little interesting that might end up helping you in your assignment. Oh, did I mention? I didn't mention. Assignment 2 has been released as well. Assignment 2 is out. Here it is. Assignment 2. Oh, Assignment 2. There it is. Implementing a Rust IRC server. IRC, Internet Relay Chat. Oh, yes. IRC is very cool. So Assignment 2 is out. And we're just going to be looking at some stuff that might help you with Assignment 2. So in particular, move closures, I think should probably help you with Assignment 2. Channels will help you with Assignment 2. And RwLock, like maybe. I can't immediately think of a reason you might want to read write lock for Assignment 2. Poisoning is just sort of generally good to know about how it works. Send and sync, we'll look at it a little more closely. And Rayon is, again, potentially my favorite Rust crate. And so we'll have to have a look at Rayon. But yeah, I am anticipating, okay, it's 20 minutes past, meaning we have like an hour 35-ish left. I'm anticipating that we'll probably be like through most of the stuff we want to talk about early. Right? Like I'm anticipating that it's probably only going to take us like, I don't know, maybe like an hour or something, or an hour 10 to get through most of this stuff here. So we'll also have plenty of time at the end for things like Q&A or just sort of general questions on older topics or generally about Rust. I think we should have room for that probably this lecture. So start to think if you have any of those. Otherwise, we'll continue as normal and work through our little to-do list here. But like, yeah, I think we've reached a bit of a turning point in the course. We've reached sort of like a bit of an apex in terms of like, you know, difficulty in concepts and that kind of thing. And so we can like sort of start to like chill out a little more, you know, some more breathing room for Assignment 2 and that sort of stuff. And and have some fun with it. So, move closures. And maybe we can briefly talk about async Rust. Yeah, we'll have to see. I'll have to also think along the way if there's a nice sort of like brief way to talk about async Rust, because you know I could make a 10-hour giga series talking about async Rust, but I don't know if I could what the best kind of like 20-minute briefer on it would be, but maybe we can have a look at it. Right, so move closures. This is more about like how do you deal with the compiler being angry at you in a case like this. A lot of the time the compiler is really smart and will tell you to put this here, but we're going to sort of figure out like what's going on here. So you might have written some code that looks a little bit like this before. So we have my string is hello. I'm going to spawn a new thread. The thread is going to do this stuff, and I just say wait for the thread and unwrap any like panics or anything like that. Right, so I just say let my string is my string. In fact, like this line, to be clear, is not necessary at all, but it sort of helps illustrate something we'll see in a bit. Let's even just leave it as println my string, and we'll see that this doesn't build. This does not build. So what's the issue here? Closure may outlive the current function, but it borrows my string, which is owned by the current function. Okay, this is like a little bit of a weird one. The reason, first of all, that I liked to put in this let my string equals my string here is because macros can do weird stuff in terms of like, often when I write, like if I have something owned, I have an owned string like this, and I say println out this and pass it owned, right? Not like a borrow of owned or exclusive borrow of owned, owned itself. Usually in Rust, we know this as like, oh, this is going to take ownership, you know, and now I won't be able to use owned again. So if I throw another println in, this will surely fail. But if I compile it, compiler's actually happy with this. And that's because println, the macro, ends up compiling this down to a shared borrow, essentially. And so, you know, when we're looking at lifetimes and weird issues going on, we want to avoid trying to like replicate specifically inside a println. So I have this, like, this seems to be enough to trigger the issue, but we'll keep the println here to sort of have a purpose, I suppose. But we're just saying, like, take that my string from main and put it in my thread. Okay, so this doesn't work. It's telling us to, like, oh, maybe move closure is what you want. Let me show you something that's, like, looks like the exact same thing. Right, so we're just going to forget about this my string and let my string be an owned string type now. And save. And it compiles. Cargo run. Yeah, it prints out. Right, so this builds, but when it's this string here, it doesn't build. Right, this string, which is a like reftick static string, doesn't build. Oh, so strange. Now, get a load of this. If I put in the little letters here, MOVE, it works again. So these four magic little letters seem to solve this borrowing issue. Right, that seems to work. All right, now, what's going on here? So closures in Rust, we talked a little bit about them, and it seemed like the chat seemed to quite like when I showed how closures tend to desugar. So in our case, the desugaring looks something like struct like my closure, I suppose. Like, you know, the way I've written it here is going to look a little bit like this. And then it says impulfin wants for my closure of whatever lifetime, we don't really care. And like, there's some bits in here. But essentially desugars into this. And the problem here is that like so you might go, why did it like throw a lifetime like this and not just say like reftick static stir, essentially? And the reason here is that Rust saw that this is a borrow, right? This here is a borrow. And it inferred that it's essentially like re-borrowing this into the into this closure. In that if I wanted to say println of my string down here again, then it's like perfectly happy with this. And we're sort of re-borrowing it into here. And in this process of re-borrowing, it's a little bit like this is kind of like a bit of a Rust stupidity in this case, in that, you know, this string might have like a, you know, might have a tick static lifetime. It might be able to live forever. But Rust isn't really seeing this because of the way it's borrowing into the closure like this. And this kind of borrowing, you know, this sort of default behavior of borrowing in a closure will always occur when the thing you're trying to like capture into the closure is a borrow in itself. So like to give her another example here, let's say I had let, let me give you a slightly different example. If I said let x is 42, and then we're going to spawn another thread, .join.unwrap, it says let x ref equals a borrow of x, and then say print out x ref out like that. This also won't work for a relatively similar reason. Excuse me. So in this case, it sees that we're capturing x as a borrow, right? Like we're capturing x here, but the fact that we take an immediate like borrow of it, the thread kind of sees like, I see, they're not really trying to take ownership of x. They would like to just borrow from it. So I guess an owned type is probably best here. They just like to do that. And again, same example down here. If I want to print it out after, the string is x, then this should still be fine as far as the compiler is concerned. However, if I got rid of this ampersand here, now the thread is okay, but this is no good, right? This is like, let's sort of like forget about the stuff up here for the moment and we'll come back to it. This is our sort of important example to look at here for now. If I have this owned string x, and then I spawn a thread and I capture x just like this, like let x ref equals x, I have then moved x into this thread, essentially. I've sent it into this thread. And then I'm like printing it out. If I try and use x down here, it goes, hey, that's no good. Like ownership was transferred over here. If I put in a borrow here, then this thread is, this closure is set to sort of capture a borrow of x in this exact same kind of way. And that the desugaring of this closure, like the captures of this closure is going to look like this. It's going to say, oh, it takes a borrow, like a ref tick a of some string. And now the thread gets pissed off about the lifetimes. It goes, hey, it might not live long enough, blah, blah, blah. We've seen the usual stuff. Now, so why did it work when I put it like this? Obviously, it breaks down here. That would be because if this is like struct my closure 1, and now I'm going to show you what the other one desugars into, instead, it'll look like this. So this closure is going to desugar into something like this, right? And noting that it owns that string, I've sort of like explicitly moved that string into the closure. And so now this closure owns the string, and then like the function, you know, when the closure call does like a call, you run the call function on that closure, it's going to grab self.myString, you know, which it owns, and it can print that out, and it's happy days. But now main is not so happy anymore, but you know, that's maybe to be expected. So what if I want my code that looks like this to still like work in the context of the thread though? Right, so now again, we've put this back in here. It says, oh, they just want to borrow of x. So we've gone back to this desugaring here. But I went, like, let's pause and think about this for a minute. What if I said the closure object itself, right? The closure object itself. What if I want the closure object itself to own the string, like we've written here, but the body of the function to just borrow from, you know, borrow from the closure essentially. So I still want this code here, but I want this desugaring semantics. And that's where this move word comes in. So what the move word here means is that anything that it sees, anything the closure sees as being captured by borrow, right? Like this here, that by default the closure will see that and go, ah, yeah, okay, they're trying to borrow that x. So I'm just going to capture a borrow like this. I'm now overriding that behavior with the word move here and saying, no, 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 I actually want you to move this x into the closure's ownership. And then the closure's body will borrow from it. So in this impl fn once, it's going to look like In fact, let me throw this. Output is nothing. And the body will look like this. Self dot, I guess we called it my string. Like this. And I apologize for all the big red squigglies. I can get rid of them if I just do that. So you see now that the closure, my closure 2, that should be, my apologies, my closure 2 now owns the string, and only when the function is called, it like borrows from it there, as opposed to the previous behavior without the move word here. It ends up looking like this with my string, and xref is just self.myString here. That's going to be, well, I guess it's still an fn once, I suppose. And like these actually, like if I wrote these two sort of implementations out by hand, these do really mean quite different things as far as Rust is concerned, right? One thing borrows from something, one thing owns the other. Usually closures are pretty good at figuring out what you want for each thing, but like when you have thread spawn, what you really need is, when you have thread spawn, what you really need is a function that doesn't borrow anything. And so throwing a move, like a move closure, whenever you're doing std thread spawn, is like pretty decidedly common, in that it's like almost always what you want. It'll just like, it will describe what you're looking for better most of the time. And so move closures are really handy for that kind of purpose. When you just want to say to the compiler, I know you're good at sometimes seeing I'm moving here, I'm borrowing there, but like really I'd like you to just move all the things. Now they're working on an idea for some sort of syntax in terms of like, what if I had another string here and I wanted to move x but not y? Like I wanted x to be captured by value by moving it, and I wanted y to be captured still by a borrow, as a normal closure interprets this as. They're working on some syntax to look like something like this, I think was the latest proposal, or it was like the proposal when I was looking at it like a year ago. In that like just move x and don't move, you know, do the default semantics for y. But there's not really a good way to express this in Rust these days. Instead, you would have to do something like, generally the trick here is to, before you spawn the thread, override the name y with a borrow to this y. There's a lot of y's going on here, but essentially here's y, right? The original thing. Now we're going to, in this scope, override the name y with a borrow to y. So then when we move y in here, it's really just this y over there. It's already a borrow. And so this is like a trick that some people might use to actually still borrow by moving, still capture by moving rather, if that's what they're looking for. But yeah, so move closures are handy when you need it. I guess I can hover over in here in Rust Analyzer to see if there's anything else sort of important. Converts any variables captured by reference or mutable reference to variables captured by value, i.e. by moving. Move closures may still implement fn or FnMut, even though they capture variables by move. This is because the traits implemented by closures type are determined by what the closure does with the capture values, not how it captures them. So this is also a really good point here, in that if I have, let's rewind a little bit here, or not rewind too far. I have this, great. Actually, let's do it like this. F is an impl for mute. Okay. So imagine I had a closure that just does like, you know, println hello, like that. I like to write a little function like this. Let me get rid of this stuff that's erroring. I like to write a little test FnMut function here, which basically just says the thing that I'm passed will implement FnMut, so that I can tell, like, if this closure doesn't implement FnMut, then the compiler will get angry at me. Like if I just say let x equals x here, it'll say this no longer compiles at all because it doesn't implement FnMut. If I didn't have this here, then Rust would just infer that this is an FN once and be fine with it. So it's a nice little trick when you're trying to figure out what a closure implements. But the important thing that the documentation was trying to say there is that in this function, like let's say I said I wanted to call another function that takes a string by ownership, takes a string by ownership, and I pass it x, right? This is not an FnMut meaning it can be called indefinitely but never simultaneously with itself. This is not an FnMut because this can only really be called once. This function takes a string by ownership. The first time this is run, it moves that string away, and therefore, ergo, if we run it the second time, it won't have ownership anymore to give to this function, and so it doesn't make sense to run a second time. So, like, one might look at this and go, yes, this is an FN once then, and the way that the Rust compiler might tell is because this because it captures x by value here, by owned x equals x, and because it captures it, captures own x by ownership, it must know that it's an FN once. But that's not quite the case, because we can still use a move closure to take ownership of x, but just because the closure has ownership, it doesn't mean it needs to move that ownership away in the body of the function, right? If all this function does is print out, this shared borrow of x, then it is still an FnMut. Note that the program is compiling now, even though it moves x away. And if I uncomment this line, it's still not going to be happy, right? And that's because the closure object will hold on to, the closure object itself will hold on to that owned value of x. And each time you call it, it's just like calling the closure with a refmut self. Right? And so that x, this string here that's owned by the closure, lives in the closure's fields, will live on, indefinitely. And so, so the owner, it doesn't actually transfer the ownership away, and so this can be promoted to an FnMut as opposed to an FN once. In fact, it can even be just an FN in this case, because it's not because it's only reading this x here. So that's the way that they worded that was: note that move closures may still print FN or FnMut even though they capture variables by move. This is because the traits implemented by a closure type, meaning FN, FnMut, and FN once, are determined by what the closure does with the captured values, not how it captures them. So it's an important one to sort of consider, and you'll probably play around with this and get a better feel for it over time. So if we go back up to the previous example that wasn't building, essentially Rust sees that this is a borrow. It infers that the type of this is a borrow. And so it goes, great, I'm going to capture this as a borrow. When really we can actually move this reftick static stir in here instead, even though we don't necessarily need to move it, within the thread itself. And now things are suddenly working again. So yeah, a neat trick when you're spawning threads, usually what you want is a move closure. And so if anything else, that's a nice takeaway in terms of, I'm spawning a thread, Rust is angry at me, you can try a move closure, and what's the worst that'll happen? You get another compiler error. It's okay, well, maybe that didn't work. Maybe your program builds and you're great, solved now. So yeah, you'll have ample opportunity to play around with these things in stuff like the assignment. Okay. So, any questions on sort of back towards closures or anything on move closures specifically, before we talk about rewrite lock and poisoning? A quiet chat today as well. Quiet chat today. Maybe something's happening on a Wednesday evening. Fine, keep your secrets. Cool. No, that's no problem. So we'll move on to read, write, lock, and poisoning. I guess maybe we'll just briefly talk about poisoning first. It's I think a relatively simple idea, but just one that's like nice to be aware of. So we talked about mutexes in last lecture. The idea that a mutex guards some value t. When you create a mutex, you need to give it that initial t value, right? They say like 0 in this case. And then the trick is you can call lock with just a shared borrow of the mutex. So, and also a mutex is send and sync generally. This bound here might be actually interesting to talk about in a little bit. But you can share a whole bunch of mutexes across a whole bunch of threads. And you can lock it with just this shared borrow that many people may be able to do simultaneously. But only one person will actually be granted this mutex guard at a time. The mutex guard, which actually gives you access to this inner t through like the deref and deref mute, basically just like how a box does it. If you recall box, box lets you access the thing inside it just by either dereferencing into a shared borrow or dereferencing into a exclusive borrow. And the trick was that when the mutex guard that you've you've called lock, you've got your guard, you've used the inner t for a few things. Eventually, when you're done and the mutex guard goes out of scope, in other words, it's dropped, internally it will unlock the mutex. It will unlock the mutex, and then someone else can have a turn accessing it, that inner t. Now there is one sort of annoying thing to work around here that the standard library sort of models in its design that sort of forces us to think about, is that when you lock a mutex, it returns a lock result. A lock result is basically just a result with potentially a poison error. Poison error. So we're talking about poisoning, poison error. Yeah, this is where we're at. So what could go wrong? What could go wrong when trying to lock a mutex? If we look at the error section, it says here, if another user of this mutex panicked while holding the mutex, then we'll get an error. Okay. So essentially, if some other thread, or whoever else, it might have even been the same thread, but if someone else has has acquired the mutex, they've called lock, and they successfully got back the guard, but before before being done and dropping the guard normally and stuff, their thread panicked. Like, let's say they accessed an array out of bounds, or they unwrapped a none or unwrapped an error or something like that, and it panicked. It'll start unwinding their code and collecting a trace back, like a stack trace of where the stuff went wrong naturally. And in that, it will end up dropping this mutex guard at some point. But it doesn't just by default unlock the mutex. It doesn't just go oh, cool, they're done with it. I mean, they're done with it in a bit of a bloody way. They've got their battle scars and everything's blowing up in front of them. And we're okay, cool, so that's unlocked now. It will sort of see that happens and then go, okay, something bad might have gone wrong. I'm going to poison the lock. So poisoning the lock so thread held the lock before it was able to release the lock. It panicked. The mutex now sets itself to be poisoned, such that whenever anyone else tries to lock it again in future, now that this some other thread has panicked while it held it, they won't get okay, here's the guard back. Instead, they'll get hang on a second, it's been poisoned. Most of the time, it sort of exists to aid in correctness. If someone needs to make sure that they fix something up, if a thread panicked while they held a lock, they have an opportunity to do that. In a lot of consumer code, where you're not writing a big library or anything, you're just trying to get stuff done, you often don't really care about the poisoning. I mean, there's a good chance that if a thread's panicked anyway, you're fine with the whole system coming down with it, because you don't really want it to be panicking at all. You'd rather see a big bright thing flashing in your eyes going, panic, 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 things going wrong, so you can go fix it. But at the end of the day, there is there is also like this clear poison, which says, oh, okay, the lock, you know, I tried to lock it, the lock was poisoned, and I want to go, no, I want to make it unpoisoned. Sadly, this is nightly, right? This is a nightly only experimental API. I am trying to recall if there is a if there's a stable way to unpoison a mutex. Whether it is I have a way that I usually do this, but I'm not sure if there's in the standard library a very good way of getting around it, and it seems like maybe the answer is probably no. So like once a mutex is poisoned, it's like kind of screwed, it seems. Sometimes you might be able to like replace the mutex with a new one, but it's a little like annoying occasionally, this poisoning. And it also means that because lock doesn't just return you the guard, you can't just go like lock, now do some stuff. You always have to throw in something like an unwrap if you don't care about poisoning, which just says this unwrap here really is saying, I assume that the lock won't be poisoned, and therefore this will be fine, and now I'll have access to the guard. But yeah, it's kind of annoying. Notably, the standard library didn't have to do this. This isn't like a requirement for like safety in general in Rust. It opens up more patterns for people to make, you know, more safe abstractions, but it also gets in the way quite a lot. And some other libraries, like Parking Lot, for example. Parking Lot is a library that provides implementations of Mutex, read-write lock, convar, and once that are smaller, faster, and more flexible. In particular, one of the things they chose to do is their mutexes have no poisoning. If there's a panic, right? If a thread is holding the lock and it panics, then it just releases the lock as normal, essentially. So yeah, I mean, that's where is our type definition, right? Yes, here we go. I'm not in the latest version. Oh, it wasn't on the latest version, whatever, that's fine. In the sense that, right, so it doesn't poison, and here's what I was looking for. Great, you'll notice that a lock just gives back a mutex guard straight away. And so, yeah, the Parking Lot API is quite nice as a consumer. I often reach for the Parking Lot API. But at the end of the day, the main idea that I'm trying to present here is that the standard library types do have poisoning. It is something that you have to deal with. It's something that can be a bit annoying to deal with as of current, based on, you know, things like clear poison being nightly. But yeah, this is what we've got. Here we go. Oh, right. Oh, sorry. The poison error type has an into inner method which will return the guard that would have otherwise been returned on a successful lock. Right. Okay. So this is the bit that I was missing here. A poison error, which is if we go back here and see we lock a mutex, that gives us a lock result. Maybe there's an error. Here's a poison error of the guard. The poison error then gives us access to into inner, right? Poison error of T, and we had a poison error of a guard, and so we can get the guard back through the poison error, but it's just kind of generally a little annoying most of the time, is what I would say. But it's a choice they made for increased flexibility for library designers, for API creators. Anyway, so that's poisoning in general. Just good to know about. And again, the very sort of high-level cliff notes is thread holds a lock, panics before it returns the lock, before it releases the lock, and poisoning signals to other threads, you know, anyone else that tries to take the lock again, that someone panicked last time, you know, when the lock was held. There you go. Cool. So that's out of the way. Any questions on poisoning or anything, feel free to throw them in the chat as you get them. Another interesting sync primitive in the standard library is a read-write lock, reader-writer lock, however you want to sort of talk about it. Reader-writer lock, read-write lock, RwLock. That's how it's commonly pronounced. And a read-write lock is kind of like a mutex, but like a little more general. in that this type of lock allows a number of readers, or at most one writer at any point in time, right? So a mutex is kind of like a read-write lock, where every time you lock it, it always assumes you are a writer, essentially. So the difference here is that imagine we had a mutex, right? We've seen a mutex here. Imagine we had a mutex where sometimes, like when you lock the mutex, you get a mutex guard. That mutex guard gives you exclusive access to the inside T through a deref mute. What if I wanted to lock the mutex, but say, hey, I'm going to lock it, but I'm only interested in reading the value. I don't actually need access to like deref mute. I don't need exclusive access to the T. I just only plan to read it. And so the mutex went, okay, what if I give a second method here that's like we have a lock, but also like it may be separated as like lock and lock mute, where it's like lock is just if you plan to read from it, lock mute is if you plan to say mutate it, you know, you need exclusive access to it. What kind of optimization would they be able to make in that case? Well, the trick here is that in Rust, you can only have one exclusive borrower at a time, but you can have as many shared borrowers as you want at a time. So if you add lock and lock mute, if you're looking for a lock mute, you need to be the only one with any kind of locking access to the thing inside. But if you only need lock, and let's say there's like another person who's already has the lock, but is just has a lock, not a lock mute, then you should also be able to lock at the same time as them. You shouldn't need to wait for them to finish, because like you're not going to get in each other's way just by reading, right? Just by having shared access. I mean, it's shared, right? Shared access. So you could imagine if you split these up in between like, lock and lock mute, you could have a million threads all locking something, or just like one thread doing a lock mute. Whereas like in the case of a mutex, it's only ever going to be one thread at a time. So there's genuinely some like considerable, concurrency and performance related advantages to be had by having a more flexible API like a read-write lock. So in particular, you'll see that instead of just having a lock function, it has a read and a write, right? They both similarly take shared access, just like a mutex. And the write will give back a lock result, right? This lock result here is the exact same thing with poisoning, right? Poisoning here. So we have to think about this result here. But otherwise, you get this write guard, and that gives you access to deref and deref mute, right? So now you have exclusive access to the inside T, whereas when you read, you get back a read guard, and this read guard only gives you deref, no deref mute. So you only have shared access. But yeah, it just means that if you have very high read contention, meaning there's a lot of time threads want to read from it, and only very rarely does anyone want to write to it, something like a read-write lock might be what you're looking for. There are catches though. In particular, one of the really scary things about a read-write lock is that depending on its internal policy, like the protocol on how it sort of deals with many people trying to lock, you can end up in really weird deadlocks. So here's an example here. Imagine you had a thread which accidentally locks, does a read lock twice, essentially. The scary idea here is that if we say, okay, lock read, it goes, great, the lock is yours, you're now welcome to read. And thread 2 here goes, I would like to write. Well, okay, that's fine. I see that you would like to write, but you're going to have to wait for this read to finish, right? You're going to have to wait for this read to finish. Once the read is finished, then I'll give you exclusive access on your own to write to the thing inside the lock. So it goes, okay, that's fine, I'll wait. So that blocks. And then thread 1, let's say thread 1, without releasing this read guard, right? The read lock here, it calls lock read again. You would probably imagine it goes, okay, well, what have we got right now? One person's reading the lock. There's someone waiting to write to the lock, but they're waiting. They haven't got access yet. So it might go, great, you're in. We'll let you read here. And it does sometimes. like that, and that's perfectly safe, to be clear. But the problem here is that if you have a system where there is like a way more reads than there are writes, like let's say there's, for every like time that a thread tries to write, there's like 1,000 times that threads are trying to read from the lock. You can imagine this write might have to wait a really long time until there's no threads reading at all. If it just goes, yeah, read, great, go through, read, go through, read, go through, read, yep, go on through, read, yes, go through, right? All this time while writes sort of just like hanging out, like, okay, is it, you know, can I go in? No, sorry, there's still some reads inside. You know, reads are all exiting the building, like they're flooding out, but there's just so many coming in that it's just incredibly unlikely for there ever to be exactly 0. Sometimes the read-write lock will implement a bit of a policy that goes, okay, the person's waiting to write here. Let's not let any more reads through for now. Like, let's say there's 400 reads in the building. It'll go, we'll wait for them to all shuffle their way out, and then we'll let the write in. Right? Any more people who are like waiting to read in future, they'll, you know, usually we let you straight through, but like we're going to say, actually, hold up for now. We're just trying to make some space for this right here. And then, you know, the reads all shuffle out of the building. Finally, there's 0 readers left. The write goes in, does the exclusive, you know, writing, exits, and then all the hundreds of reads flood back through. If that policy gets enacted, and this might be operating system dependent, it might be context dependent potentially, this kind of thing might deadlock. And then we go, reader has access. The writer goes, okay, I'd like to write. And it goes, okay, no worries. Hold on. Like, we're going to block you for now, but hopefully you get through in a little bit. And then the original thread, which is still holding this read lock, goes, I want to read. The policy might go, actually, you should wait too. You should wait too. Because we're trying to let this write out, but because it's waiting to read this, you know, to acquire this read lock here, it might not ever, it basically won't be able to release this lock until it acquires this, right? It can't release this lock until it acquires this. It can't acquire this lock until this lock's gone through, and this lock can't go through until this lock's released. So you've got like a love triangle of read-write locks that won't ever progress. And so there's potentially quite scary deadlocks that are hard to detect, based on the priority policy of how the lock is working. So like you might go like, why would a thread ever like acquire the read lock twice though? Like that's kind of like, you're kind of shooting yourself in the foot there. And like, yeah, true, you kind of are shooting yourself in the foot there. Like you probably shouldn't be doing this, but it's like pretty understandable to like see how something like this might happen. In that, like if I have some struct foo, and struct foo has like X as a read-write lock of an I32, and then on foo I have some function foo and some function bar, and they both need like read access from X. Let my X equals X dot self dot X dot read dot unwrap, forget any poisoning errors, and let's say bar needs to do the same thing. Yep, and they like both do their stuff with X. They both do their stuff with X, and this is like generally fine. Like there's not a problem with anything so far, but then we go, oh, all this code, like I wrote a whole bunch of code in both of these. Let's say like the lines of code, looks something like this, right? And then I write some code in bar, this function here. And I go like, let's say these 3 lines of code here, C, D, and E are like basically the exact same. And I go, oh, don't repeat yourself. Don't repeat yourself. That's a good design pattern to keep in mind. CDE here is just bar. So I'm just going to throw in like, just call self.bar here, right? Don't repeat yourself. And then you know, what you didn't realize is that bar takes in, does like a read on X, foo does a read on X, and that alone can cause your program to deadlock if something else ends up trying to acquire a write lock in between this one and this one going off, right? In between basically this line and this line here. So they're a little dangerous, you have to sort of keep this thing in mind. in terms of like how you would maybe solve a problem like this, I would be saying something like, well, my X is a read write lock read guard. I would say like bar inner, define another function here that takes in a borrow of that I32. Let's call that my X, I suppose. And the actual code goes in here. And then this calls self.barInner of my X, like this. My X deref. And similarly for foo inner self. My X is this. And it does the same stuff. Self.fooInner of my X.deref. And then this self.bar here instead would just call self.barInner, passing it the my X it's already got. This is like the standard approach to fixing this kind of deadlock potential with a read-write lock, in that you only do these reads and writes at the sort of very surface of your API. And then when you're like repeating yourself or calling things internally, you have like a separate space of functions. It might even make sense to put the functions all at the bottom like this, a separate space of functions that can all call each other and be happy. But there's like dangers to be aware of essentially, and things to consider when using a lock like this. But it's a pretty cool design. And yeah, we can basically just like see it through the types, how these things work, right? Like what the guarantees it gives us are and what it lets us do through the API surface. So it's pretty cool to be able to look around at it and yeah, just see what's available to us. Okay, so move closures, read write lock, poisoning, done. Channels, send sync, Rayon. We'll have a break and we'll come back to these. Channels are the most interesting of the bunch, I think. Rayon's like a probably 5-minute demo, and send and sync, like we've already talked about them a reasonable amount, so it'll probably just be like clarifying questions and stuff that anyone has, or just like poking around at standard library docs. So I think we're probably still on track to finish with things relatively early, continue to think about questions that you might want to ask. And we'll have, probably have some time for Q&A and, or maybe as Kai says, time to talk about maybe async Rust or stuff like that at the end. We'll have to see, but we'll take a quick break. Let's come back at 9 past 7:09. And yeah, we'll be back then. So see you all in a bit. All right. Oh no, it's 10 past. Oh well. Let's see this one. Cool. All right. So, channels send sync Rayon. Oh, I guess. Oh, here we go. A question. Do mutexes deadlock 2, e.g. thread A locks mutex 1, then mutex 2, thread B locks mutex 2, then mutex 1, could end up blocking waiting for each other? Absolutely. Yes, they definitely can. I'm sure we could quickly throw together a deadlock here. If we just say mutex 1 is a new mutex, just holds no data, just a unit. Then we say thread scope dot spawn for underscore in, you know, up to like, let's say 10,000 times. Do mutex 1 dot lock, mutex 2 dot lock. Let underscore a underscore 1 equal that, let underscore 2 equals that, and then the other way around, like that, 2 and 1. I'm hoping that these threads, maybe we'll do like a stood thread sleep for duration of from like nanosecond, just 1 nanosecond. I reckon that'll deadlock. Yeah, that looks like it's deadlocked. Given if I get the locks the right way around, yeah, it takes like a second or so to run. Yeah, approximately 1 second. And if I throw the locks the other way around, yeah, that's deadlocked. So yes, mutexes can also deadlock too. Mutex deadlocking is like pretty sort of like relatively well understood in the greater field of concurrency. It's obviously still an incredibly hard issue, but people have sort of techniques to get around it and to work around, to you know, work in the presence of, you know, these kind of issues, whereas read-write locks are a little more gnarly in they can deadlock in more unexpected ways, I would say, compared to a mutex. But yeah, absolutely, you can still get deadlocking with mutexes in Rust as well. Okay. Oh, that's right, there was one thing that we wanted to have a look at in the standard library mutex, which is the implementations of send and sync. So notice, that a mutexes don't implement send and sync like no matter what. They only implement send and sync if the T itself is send. So it's only okay to have a mutex of something if the thing that the mutex holds is safe to be sent to another thread. Now, why does that requirement make sense? Well, I mean, essentially what mutexes open up the opportunity for you to do is, if I have, here's like, say my main thread over here, and then I have, say, thread 1 over here. If mutexes just implemented send, send without like regard for what the inside type is, you could end up like sending any type from one thread to another. So like, let's say I had struct, I'm going to call this struct danger. Now struct danger is trivial to create. It's trivial to create one, but it's very unsafe for a struct danger to be sent from one thread to another. So if a mutex just said impl, impl send plus sync for sync for mutex, regardless of what the T is. So like impl for any T, any T essentially, send and sync for mutex. How could we create some sort of like, you know, danger in the type system? Well, imagine main created a mutex. So it's, we'll say main has a mutex of danger. Then it passes a borrow of that mutex into T1, mutex of danger, which, you know, in this system is okay because mutex will always implement send and sync regardless of the T. And then thread 1 here can say on that mutex call lock, right? That gives me a exclusive borrow of a danger, right? At mute danger. And now here's the last trick. T1, so this is the danger that came from main, by the way, right? T1 can construct their own danger, right? It's always fine to create your own danger. We were saying it's just very unsafe to send it across the thread. And once they've created their own danger, they can grab a exclusive borrow of their danger. Now they have an exclusive borrow of their danger and an exclusive borrow of main's danger at the same time. And if you ever have that, here's a function you all might not know about just yet, but a really fun function nonetheless, memswap. So if you have an exclusive borrow of some T and another exclusive borrow of that same T, then you can swap their location in memory. You can swap their location in memory. So what would thread 1 over here do? It would say swap, right? Swap main's danger, which is here, with my danger, which is here. And so simultaneously, in what it'll essentially happening is that main's danger is replaced with T1's danger. T1's danger is replaced with the danger from main. And so now they've essentially sent each other their dangers. And, you know, this will work for any type which is not send or sync. For any type that's not send or sync, we can now send that across thread boundaries through this API, which just breaks the whole point of send and sync essentially. Like, this is to say, if Rust like put in this implementation on mutex, then by using a mutex, you know, in a bit of a cheeky way, you would be able to trivially send and sync any type, regardless of if it's send or sync, whether it's send and sync or not. Which is like, that defeats the whole purpose of send and sync. So instead they actually have to say, no, it's only for T's that are safe to send across a thread boundary that mutex will implement send and sync for. So that like the only, like, sure, you can still do this with a mutex as it's written today, but only on things that are safe to send between thread boundaries. And all you've essentially done is sent one value to one thread and another value back to the other thread. So that should all be sound and safe. I believe there was a point in time where the standard library accidentally implemented send and sync on a mutex for all T's. It was something like mutex send has wrong like requirements. Rust. Do we see? Can we find this? Rust issue. Mutex send. Maybe someone can like find this, or maybe I'll have a look for it as well after the lecture and try and find it. But it was pretty funny that someone just like found this. They were like, hey, that looks wrong. I feel like I can do some pretty bad stuff with that. And they were like, oh God, you're right. There's been like 1 or 2 times in Rust's history where they've just made like a pretty serious blunder and have to go like, okay, well, you know, we're pretty committed to backwards compatibility, but in the case where like we accidentally just like tore our language a new one, yeah, we'll revert that change. But yeah, I'll try and find this after the lecture and yeah, but it's pretty funny. So yeah, I mean, like send and sync are just generally pretty interesting traits. If you have any questions about send and sync, just throw them in the chat, or if you're like still not feeling comfortable with send and sync at all, you know, any way in which I can sort of help to leading towards a bit of comfortability there. Otherwise, for the meantime, I guess we'll have a look at channels. Channels are awesome. So channels in the standard library appear in the mpsc module. mpsc standing for multi-producer single consumer. And in particular, channels give us a way of passing messages between, well, usually between threads. They don't technically need to be across threads. That's just where it's, you know, it's very commonly seen. And so the idea is, let's go back to our old faithful over here. Here's main. That's probably not going to be nearly enough space. Here's main. Yeah, there we go. That's a big main. And here's some other thread. I'm going to call it T1. Great. And main can create a channel. And a channel, like let's say it goes like, yeah, create a new channel. And this channel essentially looks like, it looks like a queue, right? I guess I'll draw the queue, something like this. I like to sort of think of channels kind of like pipes. And the channel has two ends of it. It has the receiving end. So this here is the receiver, and it has the sending end, the sender. And each of these like basically define two quite primitive methods. Like they define more than one method, but they really define one seriously important method each. Like a mutex defines, say, lock. In the sender implements the send method, and the receiver implements the receive method. So a channel, like when I create a new channel, I need to tell it like what I would like this channel to send through the pipe. So let's say it was like strings, for example, channel of string. Then what we'd get is a sender can call .send of some string, right? And whenever they call .send, it'll basically, you know, push this item into the pipe. And so it'll like end up here ready to be received. And then a receiver can call receive, and that function will block until there's a string, you know, that's been pushed into the channel. And, you know, once the sender sends something through, you know, you'll be able to receive it out the other end of this. If the sender calls send, you know, 5 times really fast, then we might end up with like 5 strings in the pipe. And then each time you call receive, it'll grab this one, grab this one, grab this one, grab this one, and grab this one, and sort of like let them be passed through to you. And so, like, again, you could technically use this with one thread, but it's most commonly used in like a 2-thread system, or like an n-thread system, really, where one thread, let's say the main thread in this case, is responsible for receiving. So it holds on to the receiver, and then it passes out the sender to other threads. So like this sender value, and so like main might launch thread 1. Thread 1 might do a whole bunch of work, and then when it's done, it goes, right, grab that sender and send back some like important information. And main is sort of sitting down here on like waiting, blocking on receive, waiting to get that information back. And then it goes, great, I got it back. Here's that like string or whatever I was after, and it can continue on. Now, if we look at the name a little more closely here, multi-producer, single consumer. Multi-producer, a producer is a thing that can send, a consumer is a thing that can receive. So these generally support as many threads as you want, like as many senders as you want. So you might have 1,000 threads, like this T1 here. Imagine you had T1 all the way up to T1000, all with their own sender that are all able to send values, but only like one receiver is allowed. In this case, main would hold on to the receiver, and every time it calls receive, it'd block until something's ready. And that might have come from thread 1, that might have come from thread 2, that might have come from thread 1000, right? Each time it gets something out of that queue. And so it's a really nice interface, and it's particularly helpful for things like, I don't know, like say implementing some kind of internet relay chat server. Channels you might find to be pretty handy. Yeah, maybe. It's obviously up to you, but when I was like doing some work on the assignment 2, the IRC assignment, channels definitely came to the rescue in a lot of cases for me, just being a very nice and handy interface. So how would I create a channel for myself? The main route is the channel function. So I like to import, like just personally, I like to import mpsc and then say mpsc channel. You could just call the channel method directly if you wanted. And this channel function will give you back, like it takes no arguments. It does have that type parameter t. So sometimes you might want to like turbofish specify it here, but other times, most of the time the Rust compiler can infer what's going on. And importantly, it gives back a tuple of two things, a sender and a receiver, both which relate to that same type, right? It's basically saying, you know, things are able to send in T's, the receiver is able to pull out T's. It wouldn't really make sense if there were two different types, because it's meant to be sent in one end and received out the other. And so most commonly you'll write something that looks like this. Let sender receiver equals mpsc channel. It's upsetting me because it doesn't know what the channel's sending. I'll just say strings for now. And now I have a sender, which is able to send strings, and a receiver, which is able to receive strings. Cool. So let's spawn a new thread. Std thread spawn. And let's say this thread, let's imagine this thread's doing a whole bunch of work. Thread sleep for, let's say like from, let's say 3 seconds, something like that. Sleep for 3 seconds and then send across, send string from, here's that work you asked for, right? So it does a bunch of work and then it goes, great, here's that information that you wanted from me. Now, we've got an issue. We've got a compiler error. Send here takes a borrow of self, a shared borrow of self. So what is the compiler inferring about sender here, right? In terms of the borrowing of sender. You know, have a quick think about this yourself. What is the compiler going to infer about how it should capture sender within that closure if it's only calling a function that takes a shared borrow of self? Well, it's going to infer that it should capture as a borrow, capture by reference. But that doesn't play nicely with thread spawn, because thread spawn needs to make sure that the data is going to live, you know, as long as it might need to. And also, yeah, I guess there's also sync here going on. That's what it's complaining about first, but we'd run into that anyway. So we know our nice new trick here, do a move closure instead. So therefore, like the sender will get moved into this thread. This thread will be able to use it and then send that data onwards. Now it's giving us a warning here saying, hey, there could be an error here. This error is basically like, if we look at the send here, in the OK variant, right? In the OK variant, it just goes, there's nothing more to do. Like you sent the message, it worked. But if the other end of the channel has like hung up, in the sense that like, let's say this receiver goes out of scope, no one's on the other end waiting to receive, then it gives you your T back. Like the T that you sent, it goes, hey, sorry, no one's ever going to get this because they've left. Everyone's left. I'll give you your T back if you want it, but you know, you might want to be aware of this. In our case, we know that, well, I mean, as it's written right now, it definitely could happen. But I'm just going to throw an unwrap there in terms of we're going to assert to ourselves that someone will be waiting to listen from them, to hear from them. And then on this end, we can say let message equals receiver.receive. Dot unwrap again, unwrapping if all the senders have hung up. There's no more sending to be done, which we know shouldn't be the case. And finally, we can say something like, we can say main received a message that says message, like that. Cargo run. I guess I never saved that. Oh no, sorry, it takes 3 seconds, of course. It takes 3 seconds. I'm also going to get rid of the read write. Oh, and it's also doing all this stuff still. Get rid of this stuff. Okay, cool. Right, so it takes 3 seconds, then it sends this message, and main is basically just waiting down here. It ends up waiting for those 3 seconds until finally the message gets sent, and it goes, great, there's that message. Now, what if we wanted to receive 2 messages? right? So we have another thread that's, you know, needs to sleep for 4 seconds, let's say. And it says, and I'm done too. And we'll say main will like wait for 2 messages, something like this. Or even we could say, actually, no, we won't do that in a loop. Oh, we could do like a for, you know, 2 times grab a message and tell us what it was. But now we've got a problem. Can anyone guess what our problem might be? It's going, hey, you had a sender, you moved that sender, it's moved into this closure, right? Here's where it was used, and it was moved because you wrote the word move, right? That's all this. Now you're trying to move it into this here, it's already been moved away from. So sorry, buddy, out of luck, that's not going to work. But hang on, the documentation said this is multi-producer. Many people can send through this channel. Like, what gives? It's not working. The trick here is that if we look at sender and receiver, right, sender, and we look at the trait implementations, what does receiver implement? Debug, yep, pretty normal. Drop, yeah, it might need to check some stuff when it goes out of scope. You can iterate over the messages that it receives, and then it says you can send it, but it's not sync. Okay, you know, whatever, just pretty normal stuff. Sender, debug, drop, send, not sync, yeah, all the usual. Clone, it implements clone. It implements clone. Yes, as Simon says, clone. I was hoping that there would be some documentation there, but it must be, here we go. Both senders are clonable, multi-producer, such that many threads can send simultaneously to one receiver, that single consumer. Great, and so cloning doesn't really do a legit clone here. It's not actually like cloning all the memory. Instead, it's basically just creating a sender to be sent to other threads that all sort of like, you know, join in the fun. In our case, okay, there's a reasonable amount going on here. The arc is sort of the dead giveaway here, but it's a little too advanced for what we need right now. So the trick is, like, before we spawn this thread, let's just start a new scope and go, let sender equals sender.clone. Oops, dot clone. Like this. Because now all we're saying is this first thread, instead of taking the sender itself, I'm just going to override that name with like a clone of it. So now that sender's intact, and within these braces, within these color braces, sender now means another sender that we can use. So when we move it in, we're only moving in our clone here. And this one's still valid to send into this thread here as well. So great. Now we've got 2 senders. Let's see if the program works. Main received message, here's the work you asked for, and I'm done too. Yay, great. Now using strings and stuff is not that handy. Like, I mean, well, maybe it is. Maybe you want to have a channel that throws strings at each other, but a really common pattern is something like enum like message, or you could imagine like for your IRC server, some kind of IRC event, right? That's maybe something like, hey, this happened, and like, here's some associated data, which is maybe a string. Or like, this other event happened, and actually the associated data here is like a ZID and their WAM, because I always loved using those as our like examples, right? Or like, actually maybe hang up now, like maybe exit now or something, right? With no associated data. Right now, if our channels are passing through these messages, main can sort of be the overall like conductor of what's going on, right? Main is conducting the orchestra, and all the threads are off doing all like the busy work, right? Maybe that's like listening for messages from IRC clients and like, responsible for all kinds of different work. But it's main that goes like, okay, I got this message, this message, this message, this message, and it's able to sort of process things in some sort of order. Channels make this kind of pattern a lot easier than they would otherwise be with shared state. And so, yeah, channels are a really great tool for concurrent programming, especially for something like your assignment. You might want to consider channels in like when you're thinking about design. Not to say you have to use channels, or if you don't use channels, you know, you lose marks or anything like that. That's absolutely not the case. But like when you're thinking about how do I want to do this, this should pop into your head and be like, maybe a channel might work. Let me consider it. There is also, so we looked at the normal channel, which is just a standard channel, asynchronous channel. There is also sync channel, which takes this bound here. This is like an interesting idea. It's probably not relevant to your assignment, but essentially it says when we create a channel by default, you can imagine that this pipe here that holds like all the messages that are like waiting in the queue to be something like a vec deck. In that, if we like only have capacity for four elements in the vec deck, and someone goes, hey, I'm going to send another message before anyone's been around to receive it, it'll go, fine, that's great. I'll like up the capacity to 16, it'll grow, and it'll be happy, right? The problem potentially is that what if your like threads are sending way more messages than the receiver is able to keep up with, right? Let's say the threads are like all together sending 1,000 messages a second, and the receiver can only deal with like 1 message a second, right? What'll happen if we just have this like infinite vec deck here that can go as big as it wants? Oh man, I'm really bad at grabbing. There we go. I got the color. What'll happen? Well, it's just going to slowly use more and more memory. It's like the queue is just going to keep increasing. Like second 1, 1,000 messages were sent, 1 message was received. So there's 999 in the queue. Second 2, another 1,000, sorry, at 1,999 messages in the queue, 1 message is received. So 1,998, right? So like this here is like a bit of a bad pattern in terms of like, if we're just looking at this pattern of like how much memory is being used to store, like to keep a buffer in this channel. You're eventually probably going to run out of memory as it just keeps growing and growing when it can't keep up with it. So maybe what you want is something called a bound channel, which essentially says, like, maybe I make a channel with a bound of like 16 or something. What that means is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 messages can fit in the queue. And then on the 17th one, like this is assuming that a receiver hasn't come through yet and popped one of these out, the 17th send that some thread does might block. It might need to wait, like this thread might be stuck waiting until there's room in the queue. And so like it's waiting. Oh, the receiver comes through and swallows a message out. Now there's only 15 messages in the queue, and so this send becomes unblocked. It, you know, pushes its message in, and it can continue on with this work. And it's actually quite a neat way of essentially letting like if we're considering this to be our main thread on this side and like a whole bunch of threads on this side, for example, it's a nice way of sort of like synchronizing them between each other, in that these threads aren't just going to run away way faster than main can ever deal with. If main falls behind, everyone will like slow down a bit to give main some time to clear stuff out, right? Because if you think about it, these threads are going to end up like blocked, waiting on it. And so in a certain sense, they are just sort of like, you know, okay, all right, we'll chill for a second, catch up, and then we'll keep giving you some more stuff to work on. So this is a bounded channel. There's some nice tricks you can do with like a bound size of 0, for example. A bound size of 0 is otherwise known as a rendezvous channel, which essentially means that if there's no space in the queue, right? If there's no space in the backup queue, if I say like we already know that if I call receive and there's nothing in the queue yet for me to take, then I'm gonna block and wait. The trick here is that if someone is not blocking with a receive yet, and I call send of some value, I'm gonna sit waiting here because again, there's no buffer at all. So there's no like box in the middle here that I can sort of store it into and keep going. I'm immediately gonna start blocking until right at the moment that another thread ends up calling receive. And then, again, no buffer in the middle here. It just goes, great, you're waiting sending, you're waiting receiving. We'll send it immediately across with no buffer in between, and now you can both continue. And so now you're sort of walking in like a lockstep motion, where it's like, okay, like, you know, whoever calls the thing first waits for the other person to catch up, whether it's receive first or send first. They're waiting for each other to catch up. That's something called a rendezvous channel, which is kind of interesting as well. Anyway, channels are a really great, a really great tool to make use of. More general idea, maybe something like message passing, if you've heard of message passing and that kind of thing. And so ask plenty of questions about channels and all that on the course forum, and we'll help you, you know, in terms of if you want to understand anything about them or have questions about how they work and all that, then yeah, we'll be able to help with that. But that's basically channels. Again, questions are always welcome. Otherwise, I guess I'll just quickly like show off Rayon being like pretty cool. And we'll have plenty of room for questions and stuff. So Rayon's so cool. PoisonError. Is there a multi-consumer version? Yeah, that's a great question. I should have probably anticipated that question. So in the standard library, no. So if we look in the sync module, you'll find that there is the mpsc module here, multi-producer, single consumer. So in the standard library, no, there is no multi-producer, multi-consumer channels, but there are in some crates. My brain is going to crossbeam and or parking lot. Let's see. So crossbeam definitely has multi-producer, multi-consumer. I'm usually very bad at reading things. Where did I see it? Or sorry, I guess they are multi-producer, multi-consumer by default is what I recall. So if I go to functions, right, unbounded, here we go. Unbounded, yes, there we go. Crossbeam channel unbounded gives us a sender and a receiver, and the big thing here is that receiver should implement clone, and there it does. So crossbeam is a very popular crate, for concurrency primitives, right? Just like it goes a little further than what the standard library does, in terms of the concurrency primitives that it provides. In particular, crossbeam also, like scope was in a certain sense ported from crossbeam into the standard library. So like a lot of people used to take scope, add crossbeam as a dependency just to get access to the scope function. And scope only just landed in the standard library itself rather recently. So, you know, people who just were pulling in crossbeam for scope shouldn't really need to do that anymore. It also works slightly different in the way that it can give back errors, I suppose. But, you know, they're there for the same sort of general purpose. I'm not sure if parking lot has channels at all, though. Parking lot is, you know, smaller, faster, generally smaller, faster implementations of the typical concurrency primitives as compared to the standard library, but I don't think there's channels in parking lot. No, there's not. So yeah, crossbeam for mpmc would be my recommendation. Cool. Yes, PoisonError. Okay, great. So consider this program here. This program sums up the first, that is 1,000, a million, a billion. So that should be the first 10 billion integers. Sums up the first 10 billion integers. Note that it's like very imprecise because it's using floats, just so we don't end up with like overflow and that kind of thing. We don't have to worry about that. But it's like the premise that we're trying to get here is that it's like a shitload of work. Like summing up 10 billion integers is no small feat. And so we'd like to see, you know, how this program performs. So I say grab 1 to 10 billion as an iterator. So that'll be an iterator over 1, 2, 3, 4, 9,999,999,999, 10 billion. And I say just treat them as F64s instead, just for the arithmetic, just arithmetic wise, and sum them up. Print that sum out. And let's run this. I'm going to run it in release mode. And we're going to see it's probably going to take a while. Josh says, what's the downsides of parking lot compared to std sync primitives, given they're smaller and faster? Is probably a trade-off if it's not in std. There has been relatively consistent effort to move some of the things that parking lot does into std. But at the end of the day, std has different goals than say like the parking lot project might generally have, in that std's like primary focus is usually compatibility, in that like if there's some bizarre platform that we said that like, hey, we want to support this platform, then they like better damn well support that platform. And so std's usually rather conservative in the things that are you know, the kind of things that it'll do and or like, you know, make use of necessarily, in that like parking lot might make certain optimizations. Like I think parking lot, for example, uses like spin locks in some like cleverly placed locations, as far as they, you know, found, in order, like, because they found, oh, actually it's a lot faster when we just like spin here for a little bit, as opposed to like relinquishing to the operating system and like letting it do the scheduling, which is not something the standard library would really want to do, because that's often like quite operating system dependent, or it might be like people might be able to construct programs that, like, how do I say this? Parking lot might be faster for like a, you know, say 40% faster. I'm just pulling up a random number that might be like reasonable for 99.9% of programs, but it might be like 1,000 times slower for that 0.1% of programs. And so would you rather, like, from the standard library's point of view, would you rather your API be, you know, a bit faster for almost everyone, but then at the cost of being absurdly slow for someone with a more niche use case? And the standard library's main focus is to support everyone, essentially. Yes, and I believe that's the case with parking lot. I believe parking lot has faster general case, slower pathological case, but someone could certainly prove me wrong. This is just like from what I recall, having looked into parking lot again, probably around a year ago or so. It's the last time I looked really closely at it. But yeah, but parking lot's pretty cool, and like I'll often use parking lot even just to dodge around things like poisoning that I usually don't really care about. And because in the kind of scenarios, programs, platforms I'm writing for, parking lot might have something to offer to me that the standard library needs to, you know, remain a little more conservative with. So yeah, that's pretty cool. Right, and we saw this, it took 7 seconds. Let's just like double check it. We'll go time release lec 14. Just to like get a slightly more accurate measurement. Actually, the other thing I wanted to do was show you this. So yeah, 6.7 seconds. Oh, come on. Oops, that's not what I wanted to do. I wanted this. There we go. Great. And how do we get rid of this thing? I need to do that. Okay. So here's what I wanted to show. When we're running this program, keep an eye on like my cores up here. So my my computer has 16 cores, and most of them are like not working particularly hard right now. There's probably 1 or 2 working like relatively hard for OBS to push the live stream out, and otherwise there's really not much else going on. When we run this program, we'll probably see 1 core goes like a little crazy. That core is going to move around as the operating system schedules it in different places. That was kind of like a bit of a bad go. Let's just like run it again. Yeah, there we go. See, this cores at 100% while everything else is doing basically nothing. And, it takes 6.6 seconds as usual. Now, the question is, like, great, that went really hard on core 14, and core 14 was able to do this calculation in 6.6 seconds, but I have 16 cores available on my computer, which essentially means my computer can parallelize, like, a program running in a certain sense. It can parallelize, like, the execution of code across 16 different, like, physical threads in a certain sense. That is to say, like, we usually think of a computer as just sort of like executing one thing in a row. 16 cores means I have like 16 spots that it can be like executing code at the same time. And like this job here, summing the numbers from 1 to 10 billion, like you could split that job in two, right? You could say, what if you add up 1 to 5 billion, I'll add up 5 to 10 billion, and then at the end, we'll just add our answers together, right? Add our answers together. You gotta press 2, 3, 4 to toggle off the other base. Awesome. Thank you. Except now my head's in the way a little bit. I'll move over here. So like I could, if I was splitting up the job of adding up 1 to 10 billion with Josh, that seems like a pretty good scheme. I'll go, yeah, Josh, I'll take the slightly harder part of 5 billion to 10 billion. You add up 1 to 5 billion. And then once we've got our answers, we'll add them up. And so like, what if Rust could take advantage of that? What if Rust could go, okay, what if we split the job up? Right? What if we split this job up and you'll take, core 1 will take the first 16th or so, core 2 will do the next 16th, core 3 will do the next 16th, and, split it up into 16 pieces and really make use of all the hardware I've got here. Right? This is a bit of a case of like, I paid for the whole CPU. I want to use the whole CPU. Right? It doesn't make like me any happier, my CPU like getting off easy and, not doing much work. I'd rather like the CPU work as hard as it can to get me the result as fast as it possibly can. I don't need to go easy on it, right? And so usually like this is doable, but it's like usually a pain. It's pretty commonly a pain. Like, let me pull up some lecture slides from 1521. Here of how this works in C, right? So this is this exact same idea of how to do it in C. This is the code. Yuck. Like, you can imagine like writing the code that looks like this in C, like just adding up 1 to 10 billion. It's obviously not going to be super pretty, but it should probably be like 4 or 5 lines of code. And now we're looking at 125 lines of code to like do it across n threads. Because it's like, it does usually suck to do concurrency and parallelism and that kind of thing. But even though like my requirement, like conceptually, abstractly, what I want is relatively simple. I just want to split this up over as many cores as I can. Right? Now, enter my favorite Rust library. My favorite Rust library. I think it's my favorite at least. Rayon. Rayon is a data parallelism library that makes it easy to convert sequential computations into parallel. So Rust defines the iterator trait, which, is a trait that lets you go like, this thing, then this thing, then this thing, then this thing, spit things out sequentially and also compose operations sequentially. Rayon also defines a parallel iterator trait, which looks exactly like the iterator trait. Like it's got all the fan favorites are in here. We've got map, we've got filter, we've got min, we've got reduce, we've got sum, we've got zip, we've got all. Like, all the normal iterator methods are all in here. But the trick is, whatever you do on this, it'll automatically parallelize across as many CPUs, as many cores as you've got. Just like, it's like magic. It's seriously so cool. Another like fun thing to quickly look at here is, so like, let's say we have a map, like where we're mapping some values. We know that on an iterator trait, it's going to go the first thing, map it, it's got that. The second thing, map it, it's now this. The third thing, map it, it's now that, right? And so if we look at the at this here, if we look at the definition of map on an iterator, we'll see that the function that maps items, from item to this new item is an FnMut. Why is an FnMut? Because we know that map will never get called at the same time, for two different elements. It's always sequential. It's item 1, map, done. Item 2, map, done. Item 3, map, done. But Rayon, well, if we're mapping with Rayon or something, now suddenly we might get it being run 16 times at once across 16 different cores. So this doesn't seem to hold up. FnMut doesn't seem right. If we have a look at Rayon map, oh wait, I already had it. Rayon map. It's an FN. That's how it guarantees that it's still going to be safe, right? So it's these pieces are coming together. This Rayon will guarantee that nothing will go wrong with the parallelism because it makes use of Rust's, FN type in this case, as opposed to FnMut, right? So, okay, let's use Rayon. I'll show you. So I'm going to say cargo add Rayon to add Rayon as a dependency. Cool. I've got Rayon now. And then I will import Rayon. So I'll use the two Rayon traits that are important to me. The trait to Rayon Rayon's into parallel iterator and the parallel iterator trait. So I'm just going to pull these traits into scope. Rust requires that a trait is in scope to call a function from that trait. In particular, like the into iterator trait, there is an into parallel iterator trait, which basically just lets me say, instead of into iter, into parallel iter, like this. And then in order to call map, which is defined on a parallel iterator, it needs to see the parallel iterator trait in scope. The reason you don't need to do this with Rust's into iter or just iterator traits is because they get pulled in by default for you, which is pretty nice. There's something called the standard library prelude, and it just pulls in things like option, things like result, iterator, clone, all the stuff that you would just always use Rust programming. You don't want to have to import every time. But now that Rayon's a separate crate, we have to pull in these two traits, and literally just to make this home, hammer this point home, if I run the program cargo or this one, right? One core is going crazy, and it takes 6.67 seconds, right? I insert 4 more characters, _PAR, save. Oops, I accidentally fat fingered Control X. Right, I've just added the word par, build it, and now run it again, and look at that. Less than a second, 0.7 seconds. And it works. Do you see that? And look at that. All the cores were being used. It's kind of tricky to time it when this window updates what it's looking at. I don't know how much bigger we can go than this. I guess we can go at least that much bigger. Oh, yeah. How good does that look? I hope this OBS still has some room. Yeah. That's all it takes. It's so cool. I love Rayon. This can wait till the end, but how does fold get parallelized? Doesn't each call depend on the result of the previous one? There's a good chance it might not get parallelized. If it's something that's non-parallelizable, just sort of by standard logical reasoning, then it'll probably just provide an implementation of it in case someone wants it, but just not parallelize it if it can't. But yeah, in fact, we can it might even say something. Parallel fold is similar to sequential fold, except the sequence of items may be subdivided before it is folded. Consider a list of... Okay, look, they've written a bloody essay on this. Docs.rs/Rayon, and have a look for this fold function. And feel free to post any questions you have on the forum. And if you post a question on the forum, I will also go have a look at it and see if I can, if I can derive anything from what they've said there. But it seems like they have quite a bit to say about parallel folding, it seems. But yeah, this is just this is a beautiful picture. just all cores, all doing. Oh, you didn't even get to see it at the bottom. I just realized. Oh no, you did, because it would have been like here, I guess. But yeah, such a cool library. I love Rayon. Yeah. All right. Let's call it there. Rayon's awesome. Rayon's the best. I mean, and Rayon really can only exist the way it does because of the way, like the way Rust is written and the things it's provided as a language. And the fact that like someone could even write a library like that in the first place, right? The language sort of is flexible enough for someone to just like do that is pretty cool, I think. It's pretty cool that this can just like exist and be a thing. It's also made by Niko Matsakis, who is a fantastic like Rust. He works on like the Rust compiler and like it writes some great blog posts. Baby Steps is like his Rust. What would you call it? This blog is where I post up various half-baked ideas that I have usually about Rust. They're often a little more advanced, but it's, you know, it's a great little blog here as well. Yeah. Anyway, so any questions and stuff before we cap things off? As always, again, we'll call this the end of the lecture. Thank you everyone for coming. Hopefully there was you know, some enjoyable things to have, you know, learned about or played around with. Any questions before I hit the stop stream button? I'll give us a minute. 10-hour async giga stream now, please. No. I don't know. So I guess we can have a look at like what so like we've just finished this, meaning we have, this is week 9 here and this is week 10. Unsafe is like a pretty cool idea. I'm not sure we'll be able to talk about unsafe as a concept for sure, which is I think the most interesting part about unsafe, which is basically the this dot point here. Writing some unsafe Rust ourselves, I think we'll probably try and pick a type that's like that needs unsafe to be written, but is still relatively simple, and try and play with that. And then it's just sort of like FFI is about calling to other programming languages like C or C++, which is interesting and requires unsafe to do so because C++, you know, other languages is inherently out of Rust's control, and so could do some very naughty things. And then just about like tooling and stuff that's available, which is just, you know, sort of vaguely relevant. And then week 10 is just like not much scheduled. So maybe we'll be able to like talk about async and stuff as a as like a bonus thing that we'd explicitly say like this is not assessed at all, but just like as opposed to me sitting in front of the camera staring at the camera for 2 hours straight with nothing to do and no one asking any questions. Maybe we could like just talk about unsafe generally here, or maybe just write some unsafe code. Another interesting thing that in the room that we might have, to be clear, we might go actually unsafe goes way over time, or like exam details took 6 hours, right? Maybe there's not as much spare time as it looks like there should be to me. But we can like plan some contingency things in terms of like, if we don't have any time, then fine, we forget it. But if we do have time, then we can plan to do this instead. I think a fun thing for that might be some sort of like live coding thing potentially, in terms of like a, you know, what would be interesting to sort of fill time and still be useful. I'm happy to like sort of sit in front of everyone and fight the borrow checker myself a little bit and, you know, write some kind of a program from scratch. You know, think about what you might like to see in the lectures, and if you have any ideas, just let us know in the course forum. But yeah, otherwise, that's basically it. I'm not really seeing any other questions. So we'll call it there. So thank you everyone for coming. Hopefully we had some interesting fun times, and we'll see you in the workshops this week, tomorrow and Friday. Yeah, we'll see you all then. And good luck getting started on your assignment 2, IRC server. Yes. Awesome. Minecraft in Rust live coding. That's a great idea. Cool. But yeah, best of luck getting started on your assignments. And yeah, we'll see you later this week. So thank you, everyone. And yeah, bye for now.